I'd like to introduce today's speaker, Professor E.H. Yang. He was the first person to receive a MEMS PhD in his native South Korea. Before joining Stevens, he was a senior member of the NASA Jet Propulsion Lab, where he was awarded the Lou Allen Award for Excellence in developing MEMS-based actuators and microvalves for large aperture space telescopes and deformable mirrors for high-resolution imaging. He joined Stevens in 2006 and directs the Micro Device Laboratory, where he facilitates student research and hands-on education in emerging nanotechnologies. Professor Yang has secured more than 35 federal grants, totaling about $8.5 million from such prestigious agencies as NSF, AFOSR, NRO, the US Army, and NASA. He has editorial board positions for several journals and has produced more than 300 journal papers, conference proceedings, and presentations, and has delivered 86 keynote or invited talks. He holds 17 issued or pending patents in the field of micro and nanotechnology, and has been elected a fellow of the National Academy of Inventors. He was also elected a fellow of the American Society of Mechanical Engineers and received the award for research excellence at Stevens in 2019. So without further ado, I'm happy to introduce to you today's speaker, Professor E.H. Yang. E.H., please take it away.
Thanks, Kevin. You hear me all right?
Yep.
All right. So I'm going to talk about magnetism in 2D flatlands. So what we do here is to develop 2D dilute magnetic semiconductors in which ferromagnetism and semiconducting properties coexist. We do this by in situ doping of TMD monolayers. Here, TMD stands for transition metal dichalcogenides. All right. So we realize ferromagnetism with a Curie temperature above room temperature, which is a critical requirement for any practical applications. Okay. Richard Feynman received the Nobel Prize for Physics in 1959. In his famous lecture given at Caltech, there's plenty of room at the bottom. He said, what could we do with layer structures with just white layers? What would the properties of materials be if we could really arrange the atoms the way we want them? I can hardly doubt that when we have some control of the arrangement of things on a small scale, we'll get an enormously greater range of possible properties that substances can have. And this prophetic remark was realized when Gaiman-Novoselov first isolated graphene in 2004, which resulted in receiving Nobel Prize for Physics in 2010. Graphene is far stronger than steel, yet incredibly lightweight and flexible. Graphene is electrically and thermally highly conductive, but also is transparent. And graphene is extremely thick, thin, of course. And there are a bunch of applications using graphene here. The range of industries where graphene research makes an impact is substantial. All right. And so 2010, there's Nobel Prize awarded, and 2010, it was probably, it's the same year, the roll-to-roll production of 30 square inches of graphene was reported already. That was 10 years ago already, all right? And the European Union has funded graphene flagship, developing several different areas for graphene and composes energy, electronic sensing, and biomedical technologies all the way toward 2030 and beyond. Okay, so what makes this graphene that great? Well, graphene has interesting and unique electronic structure. So on the right, you see this carbon lattice. Let's draw some lines across these carbon atoms. Now at the center, you have this red zone, and this red zone is called the first preorient zone. Now you see the 6 corners of this preorient zone, and the 6 corners of this first preorient zone are called Dirac points or K points. Now you look at the energy dispersion relation here, and the dispersion relation close to the K points looks like the energy spectrum of massless Dirac particles. That means electrons, once in graphene, behave light photons in mobility due to the lack of effective electron and hole mass here. So this makes electron mobility great. The theoretical potential limit of 200,000 as compared to 1900 for silicon, right? Mechanically speaking, graphene is known to be the strongest material ever discovered. Of course, it's very light. There is 1,000 times lighter than paper, and a single sheet of graphene can cover a whole football field while weighing under 1 gram. And also graphene is very flexible and is transparent, of course. And it is a monolayer, atomic monolayer, and it absorbs 2.3% of incoming light, right? So it is a great candidate to replace indium tin oxide in the future for flexible and transparent electrode application. On the right, top right, you see this sweet resistance of different thickness of graphene that are compared with those of indium tin oxide on red, right? So graphene can be used as transparent electrode for various solar cells and LEDs, and can be used as an active the material for photodetectors and so on. My own group also worked on growing graphene nano pattern graphene for photodetectors and supercapacitor and flexible substrate applications. That was 7-8 years ago already. All right. Now the thing is, graphene doesn't have bandgap. Graphene is a gapless semiconductor, which means that you cannot use graphene directly into optics and electronics. All right. So for this reason, although the discovery of graphene shows how new physical properties emerge when bulk crystals steam down to an atomic layer, there has been search for 2D materials beyond graphene. One of these 2D materials are called the transition metal dichalcogenides here, or TMDs, and these TMDs handle just like graphene. However, some of these TMD monolayers show a direct bandgap, which means that they can directly be used in electronics and optics, complementing graphene. So this development in these TMDs opens up important applications, including sensors and catalysts, electronics, photonics, energy storage and harvesting, and so on. And in addition to those, several examples, including spin manipulation using spin valley coupling, have been also demonstrated for valleytronic application and also spintronics applications. Okay. So looking at the publication record here, there has been an exponential growth in the research of these 2D materials. For example, since 2010, the number of publications per year on these 2D materials jumped exponentially. So in 2010, it was about 130, and 2018 it was over 3,000, okay, per year. So let me give a few examples here. So TMDs can be combined with graphene to form heterostructures to enable ultra-thin photovoltaic devices. And this is due to the semiconducting nature of TMD monolayers, which can absorb photons while graphene can carry away free electrons. Or one can construct atomically thin vertical PN junctions for flexible transparent electronics applications. Or one can combine several different 2D crystals, that includes TMD, of course, to render the band structure with atomic precision. So stacking different TMDs or different 2D materials makes it possible to choose the wavelength of the photons released. All right. Now, the majority of the research efforts so far have been focused on exploring exotic properties from exfoliated flakes. As you can see from these, the 4 examples they published in Nature Communications 2016 and 2017-18. Now, you do the great discovery and great science published in high impact journals, but as you can see from, for example, top left photo images, these are exfoliated flakes. Basically, you use Scotch tape or stamping methods to exfoliate and align and transfer to create heterostructures. So there's no scalability here, right? So of course, there has been another line of research toward addressing this issue of scalability using chemical vapor deposition. And these examples are heterostructure growth published in Nature Materials in 2014. And yeah, everything's 2014 here. right? But again, as you can see from the photo image on the top left, these are sort of uncontrolled, randomly dispersed heterostructures. So I would say the success was sort of limited in growing this. And better growth was achieved using metal organic chemical vapor deposition, or MOCVD, to grow monolayer over the entire wafer. Although the problem was that the small grain size, which is also another problem for electronic applications in this case. All right. Most recently, 2020, published in Science showed the macroscopic monolayer exfoliation up to 5 millimeter in size. So this is a kind of state of the art, right? With the best fabrication results that you can find in this material so far. So I would say it is still difficult to clearly answer the question how to cheaply produce large, uniform, high quality layers in heterostructures, right? So you can say yes, but you can say no. It depends on which angle you come from to see this. So scaling up is still an issue, but in addition to this scaling up issue, there are other key challenges facing this TMD research, including contact with metals, control of grain boundaries, and control of defects. Speaking of the control of defects, useful parallels can be drawn with gallium arsenides, where control over materials quality was achieved over decades of work, which means that for this TMD, which is about 10-year-old in the area, and you need probably another decade or two to achieve the control of defects. Next one in the item is air stability, which is closely relating to these defects, and control of doping alloys also related to the defects. So we worked on this doping issues to create alloys, and we learned that this enables 2D magnets, which is what I'm going to talk about today, right? So let's talk about the 2D magnets. Before talking about that, let me show, ferromagnetism. So what is ferromagnetism? Some basics here, right? That is a form of magnetic ordering in which the intrinsic magnetic dipole moment, or spin of electrons on each crystal lattice, all align in the same direction. So when you apply external magnetic field in different direction, they change the direction. But once they are removed, the magnetization does not return to its original value. This is called hysteresis. Now, when the material is heated to the Curie point, or higher than Curie point, the material loses ferromagnetism, but they regain the ferromagnetic property again on cooling. All right. Now, what if we induce this ferromagnetism to any 2D materials? Or what if we create 2D crystals with intrinsic ferromagnetic properties? Imagine that. Combined with their already rich electronics and optics, this could lead to new discoveries and applications. Okay, so that's where we come from. So this excitement is because the 2D materials largely decouple from substrates, and they allow electrical control and are mechanically flexible. And 2D materials are also open to chemical functionalization. And these attributes make these 2D magnets accessible, engineerable, and integratable into emergent heterostructures. Now, you create these heterostructures, the interplay of distinct physical property between different layers could give rise to emergent interfacial phenomena such as anomalous Hall effect and superconducting property and so on. Okay. In terms of applications, these sensitive responses of these 2D magnets will allow the development of miniaturized, lightweight, flexible, and biocompatible devices based on different magnetic properties. The thing is, there was no reported magnetism in these 2D materials until 2017, when the first observations were reported. Now, these observations were reported at only cryogenic temperatures. Again, this material in this state is not useful, right? You put everything in cryogenic chamber to see this effect, and you take it out, then it's gone. Now, they were either insulator or conductor, and they're also unstable in air. So they're gone if you put it in there. So you have to put everything in the, of course, the glow box to play with. Nevertheless, there is plenty of room to engineer 2D magnets for electronics and photonic material, because these materials can be applied and can be used as for low power spintronics, on-chip optical communications, and quantum computing, and so on. All right. So let me give you one example here. So magnetic tunnel junction, or MTJ, is one basic unit for spintronics devices. So on your right, this drawing shows the structure. So you have this 3 layers: free, barrier, and fixed layer. Barrier is basically tunnel junction, basically dielectric, and free layer is ferromagnetic property with very small coercivity, and fixed layer is a hard magnet. All right. Now, the free layer stores the information, and the fixed layer provides a reference frame here, and electrons flow through, and depends on the direction of the electron. Basically, electron has a spin up, spin down characteristic. So when you do that, it transfers spin angular momentum between the magnetic layer, and this results in a torque on the magnetization of the free layer. When this torque is sufficiently strong, it enables the magnetic state of the free layer to be changed, and thus information can be written. So that's how it works. Now, how do you make them? All right. So this is one example to create these layers. Here, cobalt, iron, so free layer, and manganese oxide, that's the tunnel barrier layer, and the cobalt iron here again is a fixed layer, looks like, right? So in order to create this layer, this is easier said than done. So basically you need facilities like that. So they put together this facility in IBM, and it cost $10 million to put together sputter, MBE, so molecular beam epitaxy, right? And PLD, pulse laser deposition, magnetron, another MBE, robotics, load lock, and surface analysis. So this type of equipment is required. This type of equipment is required for increasingly complex multifunctional materials, right? And characterization of those. So what do we do? And developing 2D magnets and characterizing 2D magnets are a lot simpler. So 2D magnets would need probably high-end chemical vapor deposition system, a lot cheaper, maybe a high-end transfer stage to stack these layers. And you stack these layers, and the stacking things have been done in the past 10 years, more than 10 years starting from graphene here. So it's much simpler, yet probably providing similar or better functionality. That is yet to see, right? Now, since 2018, there have been several review articles published in Nature and Science. This is one published in Nature in 2018 about magnetism in 2D van der Waals materials. And they gave a list of potential research topics for magnetic van der Waals materials here. And first in that list was room temperature ferromagnetic materials, which is exactly what we do. All right. So what we do is first in the list. Now, another article published in Nature Nanotechnology in the same year by Novoselov, who is Nobel laureate, about the magnetic 2D materials again. And another article here is 2019 Science, 2-dimensional magnetic crystals again. All of them say that as soon as 2D magnetic materials can be reliably synthesized with sufficiently high critical temperatures, the potential for technological impact is enormous. All right. So I want to point out here 2 keywords here. One, reliable synthesis. No Scotch tape method, no stamping method, in situ growth, large area, uniform area. Okay. High Curie temperature. So you have all these great materials, all these mass production, but the Curie temperature is cryogenic. Basically, it's useless in practical point of view. Okay, practicality point of view here. So those 2. I would like to add one more here. The journal Science suggested questions that point to critical knowledge gaps under the ground rules that scientists should have a good shot at answering the questions over the next 25 years, or they should at least know how to go about answering them. And they ended up with creating 125 questions, which was a fitting number for Science's 125th anniversary. So one of the major questions was about the magnetic semiconductors that work at room temperature. All right. So it's 2005, right? And at that time, such devices have been demonstrated at only low temperatures. And without this room temperature materials, basically, it's nearly useless, I would say. So what happened since then in this area? So The ferromagnetism in transition metal-doped compound semiconductors have been researched since the 1990s and showing anomalous Hall effect here at 3.5 K and 5 K. Okay, and then 10 more years research gave about 86 K and 200 something K using gallium arsenide, although the validity of the research was still in debate regarding the room temperature operation here. Okay, now what about 2D semiconductors? So these results are about just 3D conventional semiconductors. Okay, what about 2D? In 2D magnets, basically, there were 2 papers published in 2017 using magnetic proximity effect. So you use 2D semiconductors. These are not ferromagnets, but you put those onto ferromagnetic materials when basically these ferromagnetic properties are induced to these layers. Okay, and then they demonstrated this ferromagnetism, but again, one is 16.5 K, the other one is 61 K. Still Curie temperature well below the room temperature. Not only that, these are also Scotch tape methods. All right. Some more approaches, including doping transition metal atoms into post-processing technique into these TMDs again. Again, the problem with the scalability, and because these are doping of irons onto exfoliated, tin disulfide, right? And again, the Curie temperature is only 31 K. Now, there are a couple of papers published in 2018 and 19 showing room temperature ferromagnetism, but they are not semiconductors. And also, again, still exfoliated. And this example shown in the bottom right is MBE grown. Basically, the flake size is 10 nanometer. Okay. So we know what we need. We need 2D dilute magnetic semiconductor. We need Curie temperature above room temperature, and we need scalability and uniformity in doping. Okay. And these 3 factors have not been met simultaneously until 2020, right? So basically non-existent before 2020. There have been theory studies that predicted room temperature room temperature operation of 2D dilute magnetic semiconductors. So basically, these theory studies suggested doping of manganese or doping of irons with right concentration to these grown materials. Okay. So basically, these theoretical studies motivated experimenters, right? That include also myself. And there were 3 papers then regarding this in situ doping of TMDs. Your in situ doping means that you dope as you grow, okay? And one paper on the bottom actually is about the manganese doping. And interestingly, this manganese doping was supposed to provide room temperature operation, but actually, interestingly, none of these papers show any ferromagnetism in any temperature. No ferromagnetism, okay? So it's easier said than done. Now, what we do here is the synthesis of the ferromagnetic 2D semiconductors at a priori large scale, all right? So we use in situ technique as CVD, and it provides scalability. And first demonstration of iron doping of tungsten disulfide was done in 2018. And then another iron doping of molybdenum sulfide was done last year. And we end up publishing this last year's work first because we discovered the room temperature ferromagnetic properties, or the recently published in Nature Communications, all right? Now, what we do is iron doping, and for that, we need to use iron oxide as a dopant particles, okay, dopant sources, okay? So, but as you can see, the iron oxide melting point is nearly 1600 degrees C. That's very high. Compared to this, the reported dopants are manganese, niobium, rhenium, and their melting points are 154, 204, and 400 degrees C, right? And naturally, to dope these things while growing these materials, you have to put these dopant sources outside of the major heating zone, okay? And this doesn't work for us because we have to dope iron. So what do we do? And we learned that, or we realized that our patented technology called contact growth method actually is a very good fit for this iron doping, okay? And we use, instead of this powder thing, so for example, on the bottom, you see these cartoon showing these carriers putting moly trioxide and the dopants and sulfur, and then you put this with the powders, and depending on where you put, you put 1 centimeter more, 1 centimeter less, you get all these results, all these different results. So it is extremely difficult to control, all right? In our case, we use a thin film. So it is much more controlled, and we also face-to-face method, and we also control the sublimation, everything. So that's what we do. And using this method, we have published several articles past couple of years on the monolayer growth and heterostructure growth and stability issue. I mentioned this air stability, right? And we realized and we demonstrated air stability of tungsten disulfide directly grown on graphene, and we publish in Advanced Materials, a cover article here. And we also worked on homobilayer growth. Homobilayer means you have two the same types, like WS2, WS2, but they're bilayers. And basically you can control all these directions and everything, and we use that for electronics applications. Of course, the electronics experiments were done at the collaborators lab, not us. All right. So what we do here is to grow these, and we in situ dope irons here. So the growth mechanism is based on the reaction of transition metal oxide and chalcogen powder in the vapor phase. And of course, the growth mode is correlated with several parameters, including gas, the temperature, precursor, substrate. So this is easier said than done. It's not that simple one line of thing. You have to put thousands of hours to develop this process, of course, here. And specifically for the moly disulfide growth, the initial reaction between moly trioxide and sulfur produces intermediate volatile suboxides. And then further sulfuration of these suboxides on the substrate leads to a complete conversion into moly disulfide grain. So to do this, you put a thin film of moly trioxide onto the substrate, then context another substrate face to face. Then you send the sample is loaded up into the tube with sulfur powder placed in the upstream of the growth area for controlled sublimation. Then you purge the tube and you put argon gas and hydrogen gas at the right temperature, right time. Specifically for the hydrogen's role here, as the furnace is ramped in temperature, the reaction process begins with reduction of moly trioxide by hydrogen and the subsequent sulfurization by sulfur. And we have the growth temperature here that changes depending on what you want here. And at an optimized location, the sulfur powder is exhausted in 30 minutes here. Now, in order to dope iron atoms into this moly disulfide lattice here, we use iron oxide powder, the particles, cast onto the substrate. And then in the substrate context, the moly trioxide thin film deposited substrate face to face. And the rest of the procedure is similar, although it's different, and slight difference makes a lot of effort to tune here. But anyway, in describing, it's kind of simple. So you put argon, hydrogen, right time, right temperature, and sulfur supplied in right time, right temperature. Then furnace is held at 850 degrees C for 20 minutes before it is cooled down to the room temperature, where iron doped moly disulfide monolayers are obtained. Again, it's easier said than done, and students have to put thousands of hours into this to produce this recipe. So kudos to my students here, all right? So this SEM image shows an early terminated growth to show not fully vaporized iron oxide here. So you see this iron oxide seed with the grain, moly disulfide grains here. And further growth will make this isolated single crystal monolayers like this. And further growth will make continuous film with bilayer spots there. And with the controlled conditions, you can remove some of these bilayers. So you have larger monolayer continuous growth with iron doping. All right. So this work was published recently in Nature Communications and have several collaborators, including Stefan Stroff in physics, who is a co-corresponding author of this work. And we have also members from Columbia University and RPI and University of Rochester for various characterization, okay? So among those characterization, number one is to confirm the substitutional doping. So basically substitutional doping means you replace, so for example, you have molybdenum atoms, and you have these iron atoms, right? Iron atoms basically replace these molybdenum atoms. So that's a substitution doping. This is different from interstitial doping. You know, iron atoms are somewhere between lattice, right? And in that case, basically, you don't really realize ferromagnetism reliably. And if you have adhesion or some residues, basically it's useless. So it is important to see that the atoms are substitutionally doped. So there are several characterizations we put together here, but we show only one here. And we use the contrast-corrected STEM images of iron-doped molybdenum as well as tungsten sulfide monolayers. Actually, left side is the tungsten, the right side is molybdenum sulfide, okay? Now, in the center, it shows STM intensity spectra of the selected areas here, and where iron atoms exhibit approximately 40% lower intensity than molybdenum. Okay, so in that way, you can confirm the substitutional doping here. We use X-ray photoelectron spectroscopy. This was done at ASRC, and so figure A shows iron 2p3 peaks, and B and C show molybdenum and sulfur peaks. So you can clearly see that there is iron element, the existence of iron elements in this material, right? Now, another important measurement is photoluminescence spectra. So this is a temperature-dependent photoluminescence spectra. So on the right, especially, it shows the integrated photoluminescence for bandgap emission. So you see this bandgap emission in molybdenum sulfide in green triangle, and that of iron-doped molybdenum sulfide in red circle. But you see the strange thing, that is iron-related emission. There is a blue square that is independent of the temperature. Okay. So we scrutinize this iron-related emission here. So the pure spectra shown on the left shows the undoped sample, which is in black, and the doped sample, which is in red. And you see this iron-related emission at 2.328 electron volt, right? EV here, only from the iron-doped sample here. And this was further corroborated by DFT calculations of dipole allowed transitions. Again, what is shown here is direct iron-doped molybdenum sulfide emission from this modeling that matches the experiments, okay? Now, this iron-related emission 2.28 EV was further scrutinized using the magnetophotoluminescence measurement. So figure A and B shows a circular dichroism, excuse me. So basically you have these transition matters luminescence basically are dependent upon this left-handed and right-handed circularly polarized light, and their absorption is different. So, but this transition matters luminescence loses its circular dichroism above Curie temperature. So the thing is, you see the circular dichroism from this beta B, right? And that's a 300K. So that means it suggests that the iron-doped molybdenum sulfide is ferromagnetic at room temperature. And another proof comes from the C, which is a magnetic circular dichroism, where you applied magnetic field, vertical magnetic field at 4 Kelvin, showing the pronounced hysteresis loop, as you can see, which also confirms ferromagnetic nature of that iron-related emission. And this is because the light absorption is closely related to the Zeeman shifts, which are associated with the magnetic field. So that shows the existence of magnetic field in the material, all right? We also measured the local magnetic field of this material here, and we used the optically detected magnetic resonance spectra of the nitrogen vacancy centers. And basically these nitrogen vacancy centers are defective nanodiamonds spun onto the surface of the sample here. And you see this data point on blue shows the increase of Zeeman splitting here from 10 to 21 megahertz in the vicinity of the sample, which indicates that a local magnetic field exists in the monolayers. And the experiments done at room temperature, that means that this remains magnetic, the material remains magnetic at room temperature, all right? And the measured local magnetic field was up to 0.5 millitesla, which is comparable to the values measured in 2D chromium iodide at cryogenic temperature. The first sensational paper published in 2017, right? And that was measured at the similar level of magnetism at cryogenic temperature. Ours is at room temperature, all right? Now, The local magnetic field measurement is important to show that this effect doesn't come from some average effect of surrounding materials or some residues or some leftover ions here and there. Of course, we don't have that, but assume that we have some residues, then, if this is not local magnetic field measurement, this is kind of average measurement, you will pick up those things somewhere. But this local magnetic field means that this effect comes from these substituted atoms directly, okay? But at the same time, it is important to show average effect, because otherwise you may get this local magnetic field from section A and section B doesn't show anything. Then basically you have this segregation issue, you have this non-uniform property, right? So it is important to show also average effect. So we use the superconducting quantum interference device measurement, and the measurement was done at Columbia University. And this graph shows that the monolayer exhibits a pronounced hysteresis loop at both 5K and 300K. Of course, the magnitude of the hysteresis loop decreases with increasing temperature here, as shown in this figure here. However, the Curie temperature has not been reached at 300K, which means that the material remains magnetized at 300K again. So this is double, triple confirmation of room temperature magnetic property, all right? So again, this work was submitted in published in Nature Communication, and usually Nature reviewers are very picky. So the reviewers still want to see double, triple confirmation that there is no other effect, right? Everything has to be 100% sure that everything is from these atoms, not from other molecules, not other adherents. So what we did was to perform the additional experiments here. So basically, my student had to come back from the vacation. Actually, the first review came in December 26th, right? So that's the 2019. And then basically it's 1 and 2 months of craziness, getting these additional results. So basically that's what we did here. So what is shown here in A and B are the STM image of low mag STM image of tungsten. I'm sorry, this is TEM grid, right? So you have TEM grid, and we transfer this sample, that iron dope sample, with the PMMA. So naturally you would pick up carbon. So you see this carbon residue on figure B, and that is picked up in C and also D, right? But in the top, in the center top, that's C, and you don't see any iron elements here. This is because this EDS spectra is not sensitive enough to pick up the signal from the substituted atoms. So you are not supposed to see it. If you see it, then you may see some residues and some adsorbed material somewhere, right? So this is good. Now we double confirm that using AFM, and on the right top and the right bottom shows the optical images. As you can see, the samples are clean, right? Another confirmation was done using photoluminescence measurements using the control sample. So bottom 2 are iron dope samples, and the top 3 are control samples, basically SiO2 and the iron film and iron oxide powders on MoS2. Again, you don't see any peaks there, but you see these peaks from these iron dope samples only. Final confirmation comes from the measurement of both iron dope molybdenum and iron dope tungsten disulfide here. All right. Now, as you can see, there's no Zeeman splitting, widen the increased Zeeman splitting from the tungsten doped, the iron doped tungsten disulfide on the bottom right. The bottom right shows no Zeeman splitting, right? It stays the same. So that means there's no magnetism. On the bottom left shows a squeeze result of iron doped tungsten disulfide, and this is called the ferromagnetic. All right. So it works under magnetism, but you remove magnetism, that's gone, right? On the other hand, the iron doped molybdenum squeeze result, that is top left, shows this ferromagnetic behavior with the coercivity, right? At the center, you have this hysteresis loop, right? So what does this mean? If you pick up any signal from surroundings, right, other than the substituted atoms, then these signals had to appear also the measurement of tungsten disulfide, because we use a very similar process. We use a nearly identical process instead of some temperatures here and there, right? So we assume that the conditions are similar, and we assume that you will see the similar effects. But as you can see, you see nothing from tungsten sulfide, which ensures that actually all these effects, all these measurements come from substituted atoms, right? So this is a double, triple, and confirmation. All right. Now, what's remaining include this doping concentration. We've been unable to change doping concentrations too much, and the theory work, predicts again, lots of theory papers were wrong, and end up, I mean, they found to be wrong, right? But nevertheless, they predicted lots of change of this concentration can lead to different applications. But we were unable to do that. But interestingly, recent paper on vanadium doped tungsten selenide paper shows that low doping concentration actually helps realizing room temperature ferromagnetism. So they have hypotheses and so on, but I'm not sure that's right. But anyway, we don't know yet, right? So this is another area of research. This is interesting part. So this paper was published recently. There was almost the same time frame of our publication here. It was published in Advanced Science, and this is a very nice paper. And this shows also room temperature ferromagnetism in vanadium doped tungsten selenide here. But then the magnetic field was measured only local scale using magnetic force microscopy. This is very nice work. However, you need to think about this segregation issue. For example, this APL paper published in 2016 shows manganese doping of zinc oxide. Now, this is a quote on the bottom here from the paper. Ferromagnetic behavior of zinc oxide lightly doped with manganese coincides with the presence of manganese oxide nanoparticles, whereas cluster-free manganese doped zinc oxide behaves ferromagnetically. So this suggests that there may be segregation issue, there may be non-uniform doping here and there. Okay, so what do we do? I mean, this type of problems would affect all these doping work, right, including ours. So how do we 100% sure that we don't have this issue? I think 100% sure thing. For that, we need to create devices. So we measure anomalous Hall effects from these magnetic materials, and we do other devices such as MRAM, magnetic random access memory, from the samples taken from different parts of these wafers, and see they show similar functionality and so on and so forth. Okay. Now, in conclusion, we have demonstrated ferromagnetism with a Curie temperature above room temperature in monolayer MoS2 molybdenum sulfide here. We use in situ doping, and also we measure the local magnetic field strengths up to 0.5 millitesla here. And we confirmed the substitutional doping using STM, AFM, XPS, and Raman spectroscopy. And ferromagnetism was also measured using MCD and nitrogen vacancy sensor and screed measurements, which were also further corroborated using the DFT simulation. Okay, so I would like to give a perspective here, my perspective here. So the magnetic field strength in this material is 0.5 millitesla at room temperature. Now, this magnetic field strength is weak, so it doesn't allow us to pick up a paperclip using this material. However, it is large enough to alter the spin of electrons. What does that mean? These materials can be used to develop transistors control the spin of electrons, while the whole device maintains and remains high lightweight, flexible, and transparent. So this work could lead to a new era of information technologies with exciting applications. Those include computing, sensing, and data storage, and more. All right. So I'd like to acknowledge my students, my members, and my collaborators here. And this is a layman summary. Okay. So with that, thank you.